names and all that good stuff. Here we are. So, Galaxy Morphology, the fourth class. Thank you so much for being here. I had to cancel last week, so I hope you understand. Now I'm going to introduce a new word called morphometrics. This is an actual word. I learned from it long after I actually was working on galaxies. This turns out to be a thing in biology, but it measures complex shapes and trying to get them down to a couple of numbers. So that's what we'll talk about today. So we talked about visual morphology. We talked about the various things that you can have inside a galaxy. We talked about crowd classification. And today we'll talk about morphometrics. And so a big part of the expert classification was that you'd have one guy and he'd go over all of them. Oh, it's all guys. And so they would go over all of them and then classify them. There's also ways that if there was a larger catalog, then, for example, multiple people would do it. Usually you had Hubble's classification scheme, and so you had ellipticals, you had disk galaxies, you had disk galaxies with a bar, you had different profiles. So we saw all that already. And now we're trying to get to a point where it's like, can we get this into a cleaner, can we separate that out cleanly? Do we have to do this Searsic profile? Do we have to do this visual light classification every time? And so, for example, this was from the Galaxy Zoo. And yeah, we can do this. If we have lots of people looking at it, then yeah, it works fantastic. And so we have the red and dead and the blue and star forming. But how do we turn something like that, where we can sort of visually say, like, yeah, that's a spiral galaxy. Look, I see spiral arms, I see a bar, there's a little bit of a bulge. How do I turn that, for example, in a set of numbers so that I can turn that set of numbers in a classification on its own? So there's a couple of issues. One, you can already see that there's a lot of stars around it, so you have to get rid of those. That we sort of know how to do. Little point sources we can sort of identify and remove. The second problem is that it's sort of fuzzy, and so drawing where the edge of the galaxy is part of the problem here. And then often you have other galaxies, like the little background galaxy and the one at the top. There's a little white blob-looking thing. Like do you need to remove those, for example, as well? So morphometrics was born, and so it's a term from biology. And so this is, I love this kind of drawing, like this fantastic data visualization. It basically shows where the various points, so you define a couple of points on a bat's wings, for example. You say like, okay, we'll find these points every time and measure the distances between them. So if you have a photograph, you can do it from that. And you just click on the points, for example, that way and say like, okay, here's the bat wings like this. And so you get these different metrics, which is like, yeah, there's this difference bit or the gap between the front finger and because it's, you know, the skeletal structure of those bat wings or fingers. So you can actually say like, okay, well, the sizes are this, and like this is a good defining property to separate out different bat species. I think of it also as very simple as like you hear a point system for deer from hunters. This is something I've heard people talk about. Or fish, for example, like you see another example with fish. You like take the point at the nose, and where's the end of the gills, and where's the end of the point of the tail. And so these separations between pretty easily identifiable marks on the animal become these morphometrics. So it's like, okay, it's got like nose to gill is this long, and I know that correlates with age, for example. So we're trying to get stuff like that. So the first one is concentration, asymmetry, and smoothness. So Chris Consolis back in 2004 defined those. These were sort of ideas that were knocking around about at that time, and so he sort of put it in one scheme. We have concentration, which is the radius. So if you just put a circular radius where 20% of the light sits in and 80% of the light sits in. And that ratio, the length of the ratio that you need for 20% of the total light and 80% of the total light, that ratio is concentration. That works. That's a pretty clean definition. You do need to know where the center of the galaxy is. Usually that's not an issue. And then And you basically start counting until you've got 20% of the light and 80% of the light. So that works really quickly and really reasonably well. With asymmetry, we sort of do a second thing where it's like we flip the image and we subtract them from each other. And so that separate the difference between the original and the rotated image divided by the total image is an indication of like how rotationally symmetric. So if I flip the image and the whole galaxy disappears, it was perfectly symmetric. That means asymmetry is 0. And if I basically end up with just as much flux as I had at the beginning, so asymmetry is 1, then it is perfectly asymmetric, right? All the flux is in different places. So both concentration has a range, but it sort of goes from 0 to 10. Asymmetry actually goes from 0 to 2. And then smoothness is you do something similar where you sort of degrade the resolution of the image and then you subtract it. So you're suddenly very sensitive to like little dots in there. You can see like the little dots start popping. This is something called unsharp masking, and it's a photographic technique, so predates things like Photoshop, where you can smooth using certain photographic techniques, and then take a photograph through a smooth image, for example, you get the same idea. But the main thing is that you smooth it, you subtract the global flux, and then you are left with little dots, and so identifies how much small structure you have. That sounds great, but it is really dependent on how much you smooth in that image B. So all three of them are pretty commonly used. We also have something called the Gini parameter. If you ever were in economics or ever taken an economics class, this is a measure of inequality. So if G is 1, all the flux is in 1 pixel. So if the fraction of pixels on the x-axis and the fraction of flux. So if I get to 100%, 1 fraction of 1, so 100% of the flux, and only at the last from 99 to 100 do I go up to 100% of the flux, that means all the flux was sitting in 1 pixel. So it's an incredibly unequal it's a very unequal distribution. And if every flux has the same fraction of the flux, every pixel has the same fraction of the flux. So every time I take a new part of the galaxy or a new pixel, it commensurately goes up. That means they all have the same value. So everybody has the same, you sort of follow that straight line. And the further you are from that straight line, the more unequal your distribution is. And so that Gini parameter basically quantifies how much area there is in that gray part of the curve, between the straight line and the curve that you see there. So that is G is 0, and that is G is 1, and so Gini is somewhere between 0 and 1. It's really pleasant when things are normalized like that, so you don't have to think about, oh, wait, this is a different survey, so I have to recalibrate things like that. So this is why this is called a non-parametric. It doesn't assume Gaussian distribution, it doesn't assume anything, and it's normalized immediately. So if you want to see that in like cartoonish terms, Gini is 1, means it's a value of 1. So that's all, one person has all the money, North Korea basically. And Gini is 0. If you've ever grown up with the Smurfs, I definitely have. They all have an equal share. It's sort of like perfect socialism. So you can see how this Gini parameter is used, how, for instance, income equality is measured across the world, because it's really hard to measure income equality over different currencies and averages and like cost of living. So what you then can, for example, do is say like, well, everybody who lives in the country or state, what's their fraction of the total amount of money, for example, like what's their fraction of GDP? And if all the GDP is in one person, so you get everybody contributes 0 fraction to the GDP and one person contributes at all, then you get a Gini of 1. And if everybody contributes equally, then you end up with a Gini of 0. So that's how we can do this with fluxes as well, with pixels. And so it's a very useful, it's akin but not the same to the concentration parameter. And then we have a second one, which is the second order moments. You take a pixel and you take the radius from the center of the galaxy to that pixel. And you say like, okay, I've got the flux in that pixel. And you say, this is the flux. And then I weigh it with r squared, with the distance squared. So the further out I go, the more heavily I weigh the pixels. Considering that galaxy profiles sort of decline with radius, so that you're sort of upweighting the outskirts, the furthest out pixels. You can see the sum here. So basically you say that this whole second part with x minus xc and y minus yc, that's really just the radius. So you do the radius squared, so the flux times the radius squared and sum them all together. That's the total second order moment. And then I take that for the 20%, so 20% of all the flood pixels, the brightest one. So where do the brightest 20% sit? If they're all sitting in the center, you get you get a lower M20, but if they're a little spread out, so if you have like bright star forming regions, you get a higher M20. So that's the second thing that Jennifer Lotz is now the director of Space Telescope Science Institute. So that's what she proposed to do in 2004 as well. So that sort of gave us a bunch of parameters to begin with. And then suddenly, 20 years later, we now have Dr. Fedorov. She proposed this parameter, smoothness, which it is a little, our problem is that smoothness depends so much on the smoothing kernel. So she defined patchiness. And so the funny thing is that the words like patchiness and smoothness and concentration sort of all floated around already, but these authors put them actually on a definition. So if you have a collection of pixels that you measured with your digital camera, you can now you can say it has a number on it. And so that's how we get to morphometrics. And so patchiness is another one where we multiply the 1 over 2 pi sigma and the exponent of whatever value we have in the x pixel and the weighted or the average over all pixels and then the standard deviation over all of them. So it's really compares. If you sort of look at that, it's like, that looks like a Gaussian expression. It's like it sort of is. So it sort of compares how Gaussianish, I think, if I understand this correctly. I've only just started using these. It might actually be a good alternative to smoothness because it doesn't include an ad hoc, like I have to smooth it by this scale. You just say, well, I have this much variance in my pixels, so I'm comparing it to that. And so there is not a lot of other inputs that have to go into it. You do notice that for some of these, I need to know where the center of the galaxy is perfectly. And one of the problems for that is, excuse me, I want it to be here. So one of the issues for that is that what happens if you don't have a clear center of the galaxy? So if it's a little fuzzy thing, you sort of go like, I guess the center is here. And then all these parameters some of these parameters start shifting, and the few that are not dependent on exactly knowing where the center is are becoming more interesting because you don't have to put that information in there. If it's very clear, if it's, in this case, it's like, yeah, it's that bright little dot there in the center of the galaxy. It's pretty straightforward. But if it's a fuzzy thing that is a dwarf galaxy, then yeah, you're talking, you have an added uncertainty because you needed that as an input. So things like Gini and patchiness don't use those. They don't use the center of the galaxy, so they're a little more robust for across different kinds of galaxies. So this is the kind of stuff that, like, now we have a bunch of numbers. So we took that whole complex shape and we sort of boiled it down to about 5-6 numbers. And so we can have patchiness, Gini, concentration, and asymmetry telling us like, okay, where in this parameter space does a galaxy lie? So first question was, is CAS a good way to classify along the Hubble tuning fork? Like, can I turn the concentration, asymmetry, smoothness into, say, a Hubble tuning, as like a position along the Hubble tuning fork? Now, as you can see here, we've got asymmetry, we got a different is that a different asymmetry? Yeah. So, but the other issue is that both of them are sort of mixed. They're both mixed together. They're all mixed together. It does look a little promising in this where concentration versus asymmetry, smoothness versus asymmetry, and you can see that there are uh, giant ellipticals, early type spirals, later type spirals, but especially like if you like the ellipticals are in the top left corner. Great. The starbursting galaxies or the irregulars are in the bottom corners, the star forming. It's like there's a bit of a evolution, but you sort of go like, okay, well, that is a parameter space that if I know if I'm in this area, I know I'm looking at this kind of galaxy. So this would help automatically classify lots and lots of galaxies. Um, so it's very easily computed for big surveys. It's not computationally heavy. So this is the kind of thing that you can have your source detection or something that is right after the source detection immediately spit out. That's very helpful. So you can immediately do something if you then go like, okay, well, it's in this particular area, like it's a concentration of 6 and like a smoothness of 0. I'm basically talking ellipticals here. So you can immediately pinpoint what rough shape, what rough type you're looking at. Um, one thing that Chris really wanted to do was that to use not just low redshift, but then also move this to high redshift. Can I then do this on smaller images, but still retain this information and still get the same spread in values? Jennifer Lawrence did the same thing. So she had disk galaxies and spheroidals, and you can sort of see that, the disk galaxies sit at the bottom. So M20 at the bottom, Genie at the y-axis, and disk galaxies versus spheroidals. Like there's a clear spheroidals, elliptical galaxies are sitting to the right top of just below the dashed line. The disk galaxies sit at the bottom here, and then if you go over that line, you're basically talking about merging galaxies, ones that are really perturbed looking. And that turned out to be another very good use of these if you can identify the part of the parameter space where merging galaxies sit. You can say like, well, that way I can get rid of all the normal looking ones and I can just find how many galaxies at any given time. So if I look further back, I look at the same wavelength, but now, redshifted to redshift 0.5, 0.1, 2, that kind of thing. I'm still sensitive to this merger rate or merger fraction. I can tell morphologically how many galaxies are merging. And so you can say the fraction of galaxies that is merging at this epoch, that further epoch, and even further epoch is XYZ. And then I know how many galaxies are merging at any given time during galaxy evolution. And we thought at the time, and we still do, that merging of galaxies is a very significant impact on galaxy evolution, and it might happen so often that yes, this is actually what drives a good chunk of galaxy evolution. So identifying where and when that is happening, this was one way to do it. So you can do classify, you can like do pretty good, disk versus spheroidal, disk versus blobs, basically, and then mergers, identify those pretty well. Um, the mergers are just in a completely different part of GDM20 space. And so, but the one issue is that, sure, I can imagine that if two galaxies smash into each other, that their morphology, their morphometrics change, but then they sort of quiet out. And so you can imagine that there's a spiral collision, they merge, and eventually they're an elliptical. So how long do they spend in that above that dashed line? How long are they in that merger parameter part of parameter space? So Jennifer Lotz actually followed this up with a slew of simulations where at different times she measured the morphology of the two merging galaxies and identified how long they were visible as a morphometrically as a morphologically identifiable merger. So, for example, if you look at this, you look at T as half a gig a year, so half a billion years in. Image 1, 2, 3, 4, 5, 6, 7. If I'm looking at this, image 7, that doesn't look like it's two galaxies smashing into each other. With image 5, you got that weird arc of blue stuff. that's not a normal spiral arm. So you can imagine like, well, if I look in a blue filter, it still it's still is going to be off its normal axes. If I look at four, you go like, yeah, there's definitely something wrong, right? There's this thing looks like a butterfly. They're sort of connected up. Um, so in four, it definitely is above that merger line. But in one to three, I mean, they might be a little perturbed. Like two is the first close flyby, but not a lot. So maybe they don't get above the line in the first, 1.5 billion years of when we would consider this merger to get started. And only for about, a billion years in 4-5 do we actually see enough of a perturbance, enough of a disturbance in these galaxies or remaining one galaxy to put them above the line. Let's see if I got this playing. Okay, so simulating that visual appearance that needs to look good. And so there's a second part. You need to get the colors right, and you need to get the dust, the absorption in the galaxies themselves right. And so the duration is a whole 3 billion years, but part of the challenge was like how often, how long does it look like it is perturbed? Um, it is playing? Yes. Okay. So we got one spiral galaxy. This looks pretty good. Like this was already pretty hard to do, by the way. Something that has a spiral galaxy that rotates, actually has spiral arms. It was a challenge for a long time, and now we know how to make them. And so, of course, now we're going to break them. We're going to just smash two together. And you can see there's clearly an epoch where they are very visible in blue light, in red light, doesn't matter because if they come close to each other, new stars form. So that's the blue light. And then a lot of tidal features happen because these two galaxies exert tidal forces on each other. So you get the second merger that definitely perturbed. Look at this, but it cleans up pretty quickly. Um, there's a little bit of leftover sort of falling in, but depending a little bit how sensitive you are, those little faint outer structures, you might not catch those. They're so this is rotating around the remnant 1 billion years after the merger. You don't necessarily catch those faint streams. You do see dust in there, so that's a good thing to check for, like it's an S0 with dust, and it looks like an elliptical. Um, but there was definitely a moment where you missed a lot of the light because of the dust in there. It also changes the morphology again. So there's a certain fraction of the time that you can see it, but it means it's going on for longer. Um, so here's without dust, and if you add dust, it becomes a lot redder as well. So without dust, lots of star formation, but then add the dust in, and you see that the centers become even redder and has these like brown stripes through it. And so I'll skip the gas part, but yes, gas is another part. Like if you have cool gas or it cold cools down, then you have enough to do star formation. But if two things smash into each other, you heat everything up. So maybe everything is moved out of your detection range. So if you want to look for gas, you typically look. So this is the same merger, but now shown in gas, and the color is gas temperature. And so green is cool and purple is hot. And so you can see that, both galaxies have still reservoirs of cold gas, but the initial and then especially I think the second heat up all the gas in there to the point that no, it can't merge back down. Like it can't cool back down to look, everything becomes purple. You still have some star formation, but that's where the cold gas is. But after the last smash, like you move a whole bunch of gas out so that it's so hot that it won't be able to do star formation anymore. It's there. It's just too hot to actually fall down uh, into gravity into star formation rate. So you see that they're sort of switching back and forth now between the gas image, and then you can see that the star formation happens in where it's cool. So blue blue greenish gas, like it is here, becomes fresh star formation if it's cool enough, and there's enough of that. Okay, so this is what Jennifer Lutz did in 2010. She looked at the when is the merger actually visible. So she divided it up into a couple of steps. You know, first you end with a couple of galaxies, then there's a first pass. They do get perturbed a little bit there. And then this maximum separation out, and then a second pass, and then merge, and then post-merger. And so you can see that not every parameter is perturbed by as much. But you can see, for example, asymmetry is a good indication of first pass, and it's like right in the middle here, first pass and second pass, stuff gets really asymmetric. But it does only do that for a part of the time, like a really small part of the whole merger, but it is a very good, clean indicator that it's happening. Things like Gini, M20, sure, Gini, not so much. Concentration, sure, by the second pass you do get like a big change, but that's about it. So gas fraction, how much gas do you have? You can also look at that. If you have a lot of gas, you get more asymmetry because, hey, you got gas that starts getting tidally perturbed and starts forming stars a lot. So we looked at that later, of course, with other surveys, and all of them do seem to agree that yes, the mergers, the things that look like mergers, sit above that line, but how long you sit above that line is still, that's actually the big unknown. So for asymmetry and smoothness, you can also use that for classification. It's like you use the visual classifications to then verify where you think your area sits for mergers, for example, with asymmetry and smoothness or Gini and M20. So if you know from math that preferably for any machine learning or anything like that, you would like an orthogonal space. That means that if I change Gini, none of the other parameters go with it, but Gini and concentration, for example, are, you know, you can see that this little banana shaped. M20 and concentration, look, that's not, they're not unknown to each other. So it's not an orthogonal, meaning that completely independent parameters of these things are not independent parameters. Concentration, asymmetry, smoothness, Gini, and M20, and Paschen is very likely as well. They are correlated parameters, meaning that they're not independent. And if we want to do that, we want to do something called principal component analysis or finding the eigenvalues. Now, I don't know how much quantum mechanics anybody here has, but as soon as I say the word eigenvalues, I have a flashback to quantum mechanics, because that's when you go from a in physics at least, you go from a non-orthogonal to an orthogonal space. You have to move it to a different coordinate system. Like that's what principal component analysis is. And so Scarlata et al. 2008 did that, and she used it for star galaxy separation to find inclination effects and to discriminate between bulges and disks. And so that works okay. So it seems like a promising parameter space, like all these morphometrics. You take the galaxy images, you turn them into morphometrics, and then you have sort of the raw space, the raw numbers, to then do something clever like principal component or machine learning. So this seems like a good, what's called a feature space. So these seem to be like good things to have in your catalog to then do classifications with machine learning, with sort of like AI. I don't like the term AI because it's all machine learning, but it is a thing where you go like, I have a large data set, but these numbers are easy to get, so I can have these. I also sort of know what they mean, and I can turn this into a meaningful separation and with principal components, for example. And I have patches where like elliptical galaxies happen, where highly inclined galaxies happen, where stars sit. So here's the caveats. It's never a panacea. It's never the perfect solution. It all works great within the same survey. So if everything is the same image depth, same resolution, same wavelength that you observed it at, it works fantastic. The problem is when you want to go from one survey, for example, a low redshift survey where you know what the merger rate is, for example, at redshift 0, so locally, and then go to a high redshift survey and try to figure it out there. Um, and if you want to do that, like you typically observe a much bluer rest frame length, so suddenly you're comparing ultraviolet light to the blue light locally, and at a different resolution and different pixel scale and different, surface brightness depth. So suddenly going from one survey to another, it is very, very tricky and a bunch of things you have to control for. So as long as it's the same instrument within the same area, within the same depth and the same distance, it's okay. But as soon as you want to do changes in redshifts, it really becomes tricky. And so there's a term for that in machine learning, which is called transfer learning. If you want to go from one system where you trained your little AI or machine learning algorithm on, and then you want to apply it to a different data set, this is called transfer from learning. And so you actually need to train it some more on the new survey. And so this is sort of a similar thing happening. Yes, I can identify ellipticals from spirals pretty well in the blue light in the local universe, but then if I want to do that at higher redshift, do I still have the same resolution, surface depth of the image, and am I working at the same wavelength? So for example, if you have a spiral galaxy, you have stars, and then gas is much further out. And so this was the original idea for me to try this on gas images instead of stellar images, because I was like, well, we've got the same number of resolution elements, like the gas goes out further, but the images are lower resolution. So that seemed like a good idea. You've got a lot of anecdotal evidence that and you saw that in the simulations, but this was the anecdotal evidence from the 80s, the 1980s. So this is sort of like a whole series of pictures in 2001 uh, produced like, look, every time we look at these images and it's actually there's a big tail of gas or something, it's usually a perturbed galaxy. There's lots of evidence, anecdotal, but lots of evidence that H1 is very sensitive to interactions. So you can do that. You can define, the area that you want to do this over, the optical disk or the H1 disk, and then go through that and see how it changes with wavelength. So take a single galaxy and then do the same area and do these like Gini asymmetry concentration parameters on all of them. And you can tell that, it depends on what wavelength you're looking at. Is it the ultraviolet? Is it optical? Is it IRAC? Is it mid-infrared? Or is it that H1 map? So you can sort of step through the optical, near infrared, far infrared, and then 21 centimeter. And so get these parameters using this way. And then there is a parameter. It's like, okay, where's the nearest neighbor? And so do these two correlate? And they barely correlate. So this is very tricky to actually see in any H1 disk. And I had such high hopes. And the reason for that is that H1 disks are the lowest value and the highest value is very limited. As soon as you get to really high values, the gas essentially disappears from H1. It's no longer atomic. It becomes molecular hydrogen, and I don't pick it up anymore. So it's actually really tricky to get high densities of H1 because it just then becomes molecular. So I think that was a big part of the reason that you get that non-circular motion, like whether or not things are happening there. Part of the other thing is simply the sample. Things is the survey, and things are too quiet. There's just not enough happening in things, sorry. And so we need many more H1 maps with interactions. And so we're working on that now. The neat thing is that the other people have tried to do this as well, and you can see that with wavelength, if you have like all the models, for example, you can see that things like asymmetry peak in the ultraviolet and in the in where you see the dust, so the heated star formation. So either the original blue light from the stars itself or the dust that it eliminates. And so you notice that, yeah, if you're just looking at normal stars, that's actually when your asymmetry is the lowest. Genie is sort of the flip side of that. So that was an interesting like comparison with somebody trying to do this with different Hubble types and to look at that in the local universe. And so the trick being like, can morphometrics be compared across surveys? Adam Reynolds did that in 2020, and that was with H1. And the trick is every time, because all the so this he just looked at asymmetry, nothing else, just various definitions of asymmetry. The problem is that if you go from one survey to the next, the resolution changed, the pixel scales change, the sensitivities change, and suddenly even the same galaxy doesn't look exactly like the same galaxy anymore, and the asymmetry changes. So this is clearly a challenging thing. So keep it within one survey was another conclusion from Reynolds. So can they be compared across surveys? No. I find that the subtle differences sort of change everything, and that can affect your end conclusion, saying like, oh, there's way more mergers happening. It's like, oh no, I was looking at UV instead of optical. So, and if I move into the UV, locally even, I get way more asymmetric galaxies. So this machine learning has a very similar problem. I just said that already, but like from one data set to the next, it's called the transfer problem or transfer learning. If one adapts the machine learning algorithm that you've first trained on one set to now operate on the next one. If you fail to do that, yeah, there is going to be a problem. And so I tried it with larger surveys. And so the Westerbork H1 spiral project, WISP, and also try to look for things like morphologies that were classified as lopsided. And so lopsided means something else than asymmetric. Asymmetric can mean that the flux is just, the one half is not the same as the other. Lopsided is that the galaxy is much more pronounced on one side than the other. So once again, we have asymmetry, Gini, M20, and whatever parameters you want us to define. GM is something I tried to define myself, didn't quite work, but you have these literature criteria and you have the H1 criteria, and with H1 you can identify lopsidedness pretty well. So once again, you're sort of looking at statistically identifying most of the sample. That was the original goal. So you can say like, well, I get a good handle on the fraction, maybe not individual galaxies, but the fraction I can get a good handle on. And with machine learning, actually, we're trying to take this a step further, where we can say like, well, not just that, I want to be able to say this particular galaxy, I want to give you a probability that it is lopsided based on your morphometrics that you've measured. For example, M51 is a very well-known interaction. Where does it sit? It sits always in that interaction, in that merger box. So merger criteria, you get them from the literature, from Gini and M20, from Chris Consolis and Jennifer Lotz, and then the H1 specific ones are defined differently. So, but how long are they there? And so the part you then have to do, and you basically have to do for every survey or every wavelength regime that you're doing this in, how long does asymmetry, like how long is a galaxy asymmetric if it's merging? So you take simulations, exactly what Jennifer Lutz did, and then as you see the merger happening, like on the left side, you see where the gas is, on the right side, you see the temperature. And so you measure how long it looks asymmetric in gas versus in stars. And so that's what we did. Oh, was that a movie? Be very careful. Yeah. Okay, so those were just pictures. Sorry, I can't remember where I put a movie and where I just put the pictures. So you had these simulated H1 maps. These are really hard to do in simulations. We're only now getting reasonable ones. You can see that these don't have much spiral structure. And I was hoping for more of spiral structure, because if you look at an H1 disk, you usually get lots of spiral structure. But as they merge, you can see like, well, I get lots of asymmetry. And if I just keep the isolated disk going, it's pretty symmetric. So I can look at how long is my asymmetry above that line that Chris Consolis drew. And it's like, yeah, it's above that for much longer than it was with the stellar disk. The stellar disk is not as much affected. M20, same thing. GM, not so much. So if I can use asymmetry or MM20, for example, I can say like, yeah, this is when I've identified it as a merger. And so it's out of the 2.5, 3 gigayears of an interaction, about a third of the time it's visible. So the selection is much more reliable because I see the merger happening with morphology much longer. Does that make sense? All right. So simulated and isolated disks that seem to be working okay, but the trick is that, yes, once again, we're dealing with transfer learning. So we're going from actual data to artificial data. And did we actually take everything into account? Okay. And so you see that sometimes the whole thing has shifted a little bit because, yes, computing the asymmetry in a artificial H1 disk versus a real H1 disk can matter quite a bit. So some of these work, some of them don't. That's sort of the whole point of this slide. But the visibility time is like 1 out of 2.5 gigayears. So the variance is substantial, but yes, it's visible for longer. So this might be a viable way to do it. And selection is typically during the first or second pass, so very much like we saw with Jennifer Lutz's results in 2010. The asymmetry spikes during the first and second pass, but it spikes longer in the H1, in the gas part. So you can actually identify them that way. Another thing that you can do with morphometrics is look for these extended ultraviolet disks. And as you can see on the right here, the UV is the black image, the gas, the H1 is the contour. And so which one of these little black dots belong to the galaxy? That's really an issue because you can sort of see some of those dots might just be a background galaxy. Some of those do belong to the galaxy, and it's hard to pick those out. And the red dot, the red circle, circles the furthest black dot that the authors thought was belonged to this galaxy. And so anything that was further away probably didn't. But they sort of had to eyeball that. Well, can we do that better? And it's like, well, you can cut out the H1 contour and say this is all the H1 disk, so all the little black dots that are in there are star-forming regions in that gas disk, so they belong to this galaxy. And so you can find extended UV disks, known as XUV disks, that way. You can do it with concentration and asymmetry, or M20 and asymmetry, and say where do the various where do those lie? So this is the kind of thing what you can do is like you define in a single survey, this is how I define my morphometrics. Then I have my morphometric space, and in that you can identify, for example, a subgroup that you're interested in. You've got a few examples, that's your training set, and then you can sort of get the rest of them. So that works reasonably well, it seems like. So morphometrics is a seemingly straightforward way to turn complex morphologies into a few numbers. Plus side, I have a few numbers. Downside, I only have a few numbers. You are boiling a complex thing down to a few numbers. If you've ever made your own clothing or try to go shopping in a different country where they suddenly have different numbers on all the clothing, it is the kind of thing where you realize, yeah, I'm actually not just two numbers. I'm just going to have to try a few things. So part of the issue for morphometrics is that it does throw some information and subtlety away often. You are boiling it down. It depends very much on the depth of resolution and the wavelength observed. So if you have a survey, you have to say, okay, it's going to be in this band within this survey at these distances. So I know what resolution, what physical resolution I'm working with, what the depth is, what the wavelength is. And I can absolutely define things within that. That works really well. But if I really want to go from one survey to the next, I have to be very careful to match both depth, resolution, and wavelength between the two. Otherwise, there's going to be subtle differences, and that can be very tricky. It is a good broad discriminant between spheroidals and disk galaxies. That's great. It's good at identifying mergers. That's fantastic. Getting it all the way down to a Hubble type,
trickier. Like that's the level of resolution, that's the kind of level of information that might not be in there. It's a good parameter space together, for example, with a Searsic profile, because a Searsic profile does not take the distribution of H2 regions, the distribution of star formation, very much into account. Like it's just, this is the radial profile. It smooths it out radially. So you sort of get a broad profile, and then all these morphometrics tell you how much substructure there is. It's a very good feature space for machine learning projects. I've been doing that for a bit now, and it might be very useful to identify rare objects. If suddenly you have like a combination of morphometrics that are all the way out in left field, that's an interesting object. We should take a look at that, right? So not just what the average is doing, but also the outliers are very interesting. So as you can tell, this is something that I've done some research in, that my grad school friends and cohorts have done research in. It has become part of the toolbox. It has moved away from a direct thing that we measure and use to a feature space that we then use machine learning on. But the best part is it's easy to, if you have a lot of images, it's easy to compute, and then it's not a big catalog, and that catalog is then easy to run different kinds of machine learning on. So it's fairly easy to optimize and to use and to learn machine learning from. So yeah, I find that a useful component of this. So this is all the kind of machine learning that you do before you go neural, as the speech goes. So neural is when you feed the images in directly and then do a neural network, and or multiple layers of a neural network in order to then get a classification, for example. This is sort of takes that first step, images to catalogs, and so that reduces the amount of data that has to go in. So suddenly you can train it on a normal computer rather than a data center. So that's a big pro for these. Okay, that's what I wanted to talk about. Morphometrics is a term that I'm trying to make happen, like fetch in the movie Mean Girls. But I think it's a good way to phrase this, and this has become a good tool for us all to use. All right, any questions? It's okay. It's Thursday afternoon. It's all good.
I do have a question about something external to what we've talked about. So I'm starting my grad school applications because they've just opened.
Mhm.
I have one that asks for an official transcript copy PDF from the student. And I have one from January. And I don't know if that's too old, even though the information is the same.
Official copy transcript. I oh, there seems to be no good standards for these. So I'll be honest. I'm just going to stop the recording because this is no longer